Now that we know how to take partial derivatives of functions, what I'd like to do is reconcile what the idea of a partial derivative is with the notion that we have for the regular derivative of a single variable function, df dx, at a particular point a. So in previous slides, we've seen that when you're looking at a function of a single variable, say f is a function of x, and we look at this quantity, df dx, otherwise denoted f primed, at a particular point x is equal to a, what we are interpreting this value to be is the slope of the function f at that specific point a. What I'd like to do now is show you how partial derivatives generalize that philosophy. So what I have here is this picture of a surface, and what I want us to think about is that f is now a function of two variables, x and y, and we're going to plot the output of the function f of some specific point A, specific point B, by this z-axis, and its height is shown on this surface right here. So the surface here it's seeing is the collection of points that are the outputs of all the various x and y inputs you could obtain by plugging them in to our function f. Recall that when we take the partial derivative of the function f with respect to x, we pretend that the y variable is a constant. If we think about taking some specific y value, say like y is equal to 0 here, and plugging that into our function f, then that function f would become a function of a single variable, and it would be this green line right here. If we then considered a particular point for that fixed y value, then if we compute the partial derivative of the function f with respect to x, what we're going to get is a measure of the way that the function is changing along this green line for various different values we could plug in for a. So if we go even further, fixing a specific value for y, and then plugging in a specific value for x, what we'll obtain is a single point right here on the function, and the value of the partial derivative of the function f with respect to x, evaluated at that specific point, will be is the way that the function is changing in the x direction at that particular point. Similarly, if we were to look at the partial derivative of the function f with respect to y, evaluated at this same point ab, what we would obtain is a slope value which indicates the slope of the tangent line running in this direction if the x is staying constant and the y is allowed to change. And what that would be representing is the slope of this surface at this particular point as we head in the y direction. So it becomes a little bit harder to visualize functions of several variables, but if you're able to come up with a picture of them, and you think about the process of taking a partial derivative of that function with respect to a single variable, realize what you're doing is viewing the other variables as constant so that they are no longer moving. That reduces you down to this single variable case, and we're back in the position of finding slope again, just slope only in one direction. Changing to examine partial derivatives with respect to your other variable will give you the slope of the function at the same point, just in a different direction. Now there are many other things we could say about partial derivatives. I'm going to mention just two of those facts right now that we'll particularly need as we move forward in our applications towards data science. The first is that one property that we really care about from functions of a single variable with respect to derivatives also carries over to partial derivatives, and that's the additivity of taking derivatives. So if we have two different functions of a single variable, f and g, both of which are functions of x, and we wanted to take the derivative of the sum of those two functions, that plays very nicely and does exactly what you would expect it to do. The derivative of the sum of those two functions with respect to this single variable is the sum of the derivatives. Never fear, this property carries over to partial derivatives as well, so all I have to do to move from single variable calculus to multivariable calculus with this particular property is change my straight Roman D's to the curly del's of partial derivatives, and that same fact holds true. Derivatives, even partial derivatives, respect addition. So the second thing I'd like to mention is that there's something called the gradient vector of a multivariable function, and all that is a full list of all possible first-order partial derivatives of that function. For the example we worked with in the previous slides, which was a function of two variables, x and y, we would look at this vector of partial derivatives, first the partial derivative of f with respect to x, then the partial derivative of f with respect to y. If we were working with a function that had three variables, we would have a gradient vector with three different components, one component for each input variable of the function. So that list of partial derivatives, which we're thinking of as a vector, so we're using these angled brackets to contain those partial derivatives, is again called the gradient vector of the function, and it's denoted with this upside down triangle, the gradient vector of the multivariable function f.